So next up is Jeff Rousseau from Aptima to talk about multi-robot systems with ROS.
So I'm Jeff Rousseau. I'm a software engineer at a company called Aptima. We're a research and development firm based out of Boston, Massachusetts. I'm also the coordinator on the Multi-Master Special Interest Group. And this topic came about because over the past few years I've been struggling with issues in my lab trying to get my robots to communicate with each other over lossy Wi-Fi connections. So basically I'm just a software engineer trying to scratch an itch. I'm going to preface this talk with a big warning. A lot of the techniques I'm going to mention today should be considered experimental. Much of the code in the multi-master, multi-robot domain is the wild type, in that it's written for a particular prototype test case generally, and then left largely untouched. That said, there's a lot of code that's out there that does exist and does work in its present state. I'd like to point out that I'm not claiming expertise in all networking technologies, even those relating to the current master implementation. So I'm not a master in all things master related, and I welcome you to question my assumptions because I'm just a single engineer in a single lab out of very, very many. The goal of this presentation is to shed some light on how masters presently work. This topic seems to be an area of confusion for a number of users. With ominous names like master, it can be a bit confusing as to what the actual role of a master is in a ROS system. Another goal is to provide a simple solution for sharing limited topics between unreliably connected robots, such as mobile robots that are in a field trying to communicate with each other. I'll present some ideas for some future directions. There are a number of interesting ways we can go with the master system in ROS, including, as what I'll mention later, possibly getting rid of masters altogether. And finally, I'd like to raise some awareness for the multi-master special interest group so we can nail down everybody's use cases that we need to support, ideas for implementation other than my own. So why run multiple masters? And I'll give you my biased perspective. We'll talk about what a ROS master is, what its role is, when to split up your ROS system if it makes sense to do so, and some ways to do it. I'm going to cover primarily the foreign relay method, which has been wrapped in a number of different packages, and I'll mention some of those. I'll also note some, make some notes on ROS transports. They're not really part of a multi-master solution, but they're usually lumped together in the same category because when you're dealing with multiple robots, you're dealing with connections, and connections tend to be a cause for concern when dealing with multiple robots. So I'll discuss some limitations on the current master implementation and some ideas for the future. So in a perfect world, everything is connected all the time. Robots are connected to each other, the internet, everything. Robots never unexpectedly go offline. Their batteries never die. They never wander into dead spots on your Wi-Fi network. Bandwidth is plentiful, and everything's great. And there's no latency in the system. But unfortunately, when dealing with multiple robots, especially connected over Wi-Fi, in the real world, we can't assume persistent connections. Machines go down suddenly, things crash, run out of batteries, etc. And bandwidth is usually severely limited, especially in the field when we're dealing with networks like 802.11, like A and B and stuff like that. So high bandwidth topics, sharing high bandwidth topics between robots like TF, point clouds, HD video, they'll easily take up the majority of your bandwidth between robots. So a note on some transports. This is, like I said, this is not a multi-master topic really, but it always comes up in conversation. So the primary transport, it should be noted that ROS is TCP-based, which has a lot of, excuse me. It can cause some issues. So there are certain times when TCP isn't the best choice for communication transport between robots, especially when latency is prized over reliability. So TCP is a reliable transport. Things like UDP, multicast are not. So you might want to, for operation of robot over teleop, you might not care about the reliability of those messages. You might not care that a message is coming in several seconds late because it did a bunch of retries. That message is old and it's not very useful. Same thing with audio and video streams. So you might not care about getting every frame. TCP is unicast, meaning you need a connection to every machine. If you have many nodes receiving data from relatively few publishers, like a one to large N, multicast protocols start to make sense. So I started to look at a PGM solution, which is a pseudo-reliable multicast solution. But that's just a small aside to the conversation about multi-master. So let's talk about what a master actually is. It's an XML RPC server. That's an implementation detail, but it's a kind of important one if you need to know, if you need to debug what's going wrong in your system. You can kind of think of a master as DNS. It's where nodes go to advertise a given topic and type, so it's a dictionary store of connection information and topic names. Subscribers also go there to find their publishers, and service URIs are also stored there. And the master is often bundled with a parameter server. So ROS core is actually a instantiation of ROS launch that creates a ROS param server and a master server. So let's walk through an example of how a master transaction works. So here we have a camera node and an image viewer node trying to talk to each other. So the camera node says to the master, I would like to publish this topic of this type, and the master takes its connection information for its slave XML RPC. And then the image viewer comes along and says, I would like to receive images on this topic. Is there anybody advertising? And the master says yes, and he gives it the connection information. And then they build a connection to each other. And now the transaction to the master is done. So let's do a quick experiment. So I have a, let's see if I can find my mouse. So I have a Ubuntu VM here. Where's my mouse? There we go. So if I run ROS core here, okay. So basically what I've taken here is I have this package that it's basically the tutorials for making a simple publisher and subscriber. And if I run the talker, start spitting out string messages on a chatter topic. And similarly, here's the listener. It's receiving all those messages. So what happens if the master goes down? They're still transferring. So since, like in the diagram in the presentation, the master transaction is over, and these guys are still communicating with each other. But there's some issues. So what would happen? Actually, let's first try and do a ROS topic list. And we can't, because there's no master, because the master stores all the information for all the listing. So if we start up a new master, and we do a ROS topic list, there's no nodes. So these guys are orphaned. There's no way you can add new listeners to these topics that exist and are transferring data. So basically, you're kind of in trouble right now. And even if you tried to do ROS node kill all, it just killed ROS out. These guys are still running. So you have to be very careful about this type of stuff. So if you take your master down and you're trying to debug something in like RViz, and you restart your master, all those topics that you were hoping to look at are not going to be there. So it's a very common problem that I've run into. So what did we learn? Let's see. So if we lose our master, publishers and subscribers with already established connections continue to work, sort of. If masters can't return, say they were on a foreign machine that's down, we can't add new subscribers to the existing publishers. We can't call any ROS services or access any ROS parameters. If we start up a new master, the old nodes are orphaned. There's no way for the master to have any idea that they even exist. So ROS topic list, et cetera, all those tools, they won't work. So going from a single to multiple masters. So most nodes that rely heavily on dynamic parameters and setting up new nodes on the network will not fail gracefully if the master is intermittently offline. So you say you have a Wi-Fi connection to a server, and it's kind of flaky. This situation wouldn't be very useful for a robot with high autonomy that's trying to get work done. Another situation, and one I deal with in my lab, is if your robot wants to connect to services that it doesn't know about at configuration time. So right now, a master needs to exist for publishers and subscribers to basically start doing their jobs. So if you have a robot that's wandering into a lab that has a server with a service on it saying like, I have a map, that ROS system on that server has to exist independently of the ROS system that's on the robot. So these are two reasons, possibly some debatable good reasons for having multiple masters. So what I'm going to talk about is foreign relay as the main basis for sharing topics between two ROS systems that are running their own masters. So let's peek under the hood of foreign relay. So there we go. So here's one ROS system. This is a VM again. And what we're going to do is we're going to start another VM. Hopefully. Okay, so this guy's running a ROS core right now. We're going to close down this stuff. So we should be in a happy state right now. ROS topic list. Yep. And on the other machine, we'll do the same thing. Now what we're going to do is, so just imagine that these are two separate robots, or a robot and a service on a separate server. And we're going to run cores on both of them and forward the chatter topic from the tutorials from one to the other. So the node I'm going to run right here is called foreign relay. And if we look at it, it takes in whether or not you're going to advertise to a foreign master or subscribe, the topic, and then the foreign master URI. So we're going to advertise our chatter topic. Let me make sure I'm on the right machine. So if we go over here, we now have our chatter topic. So we have two separate ROS systems talking to each other over a foreign relay. Which is pretty neat. So let's look at what foreign relay is actually doing under the hood. Oops. So one of the first things you might notice in this Python node is it's actually not a node. It's not using the ROSPy client library. It's actually calling XML RPC calls directly. And that's pretty much all this thing's doing. So if you look in the main method, basically all it does is do a parse on the arguments that you pass it, and then call the go function. So basically, all it does is get all the published topics from the master, and then it iterates through until it finds a match on the topic type, and then it iterates through and finds a matching publisher. And it does this at a pre-configured rate. Right now it's 1 hertz. And all it does is try and sync the state between those two. And if you do a, so that's what these two lines are doing right here. And if it sees any differences between advertising and subscribing between these two foreign masters, between these two masters, it syncs those differences and unregisters where necessary and registers where necessary. So what are some of the limitations of foreign relay? So the primary one that I've found, at least in my use case, is that you need to know the state of your ROS system at configuration time. As this is a node, you have to write a bunch of launch scripts, basically, that are going to relay the topics that you care about to the machines that you care about. So you have to know about those machines ahead of time, which kind of defeats the purpose. There's also no good way for nodes to know when foreign masters go away. So if other than attempting to make service calls and then catching exceptions, but that's not a very clean way of doing it. On a related note, there's an old issue in the master issue tracker about adding time to live to master registrations, which might be worth revisiting. If implemented, you might be able to detect and notify subscribed nodes when their subscriptions have expired. And I mentioned that there's no programmatic interface to foreign relay. So some people have made some clever workarounds. This is a current popular workaround that's used in Wi-Fi comms, which is something that wraps the foreign relay into a more general, more full-blown multi-master system. And basically, if you look at the code, it's basically just running the command line tools through code. It's a hack, but it works. Another approach, which is one I've been working on, is to actually use the multi-master approach in ROS Java, where you can, unlike most language bindings like ROSCP, CPP, and ROSPy, Java allows you to programmatically instantiate masters, and nodes can be pre-configured to attach to a given master. So each node can be configured to run on any number of master, whether it's foreign or local. So this leads to some interesting applications where that can span master boundaries when paired with service discovery mechanisms like zeroconf. So here's an example code snippet from ROS Java showing a node and a node runner being instantiated with a connection to a particular master. Next, I'm going to show you an application I built using zeroconf service discovery to detect foreign masters and launch runners programmatically on the ROS Java side with connections to each of those foreign masters. So this is basically just a diagram showing that. So each machine in this system runs its own ROS core, including the tablet itself. So I have an Android tablet running a ROS core and zeroconf, and then I have 3 robots, or I've only gone up to 3 in my lab, but because that's what I'm limited to. But 3 robots running around, and if I took a new robot into my lab running this stack, the Android interface would detect it through zeroconf and then attach to its master programmatically. And this is a video, and maybe it'll work. So this is So this is me just doing some testing of the Android interface. Right now, this is done with simulation, but we have 3 Turtlebot-like platforms running around our lab right now. So this is running an HTML5 interface on top of the Android ROS Java, which is running its own master, which is connecting to that simulated navigation stack through Stage, in this case. But it works just fine on actual robots as well. Some notes on this application. So ROS Java only supports TCP as a transport, at least for now. So if you rely on being connected to, or actually if you rely on trying to transfer compressed image topics, for example, over ROS Java, it won't degrade very well as the connection gets bad. So if you go to a place with a weak RSSI in your wireless network system, bad things will start happening. But hopefully this will be fixed in the future. On actual robots, I need to throttle a number of topics, especially TF stuff, like pose messages coming from AMCL, to get a decent response time. So a lot of TF stuff over Wi-Fi can cause a lot of issues, especially if you're doing TCP transport. So some ideas for the future. One idea is to have like a public master. You can kind of think of this as a sort of bridge, which would only expose topics that would be interesting and useful to foreign ROS machines, which would be also running their own public master. This would be geared towards limiting the availability to only public APIs to foreign machines. And to credit Morgan, the idea of hierarchical masters. So it's kind of building on the DNS metaphor. So a supermaster could have like sub-masters, etc. And a related idea, like I said, not strictly multi-master, but improving transports is a pretty important thing to do when dealing with flaky Wi-Fi connections. So UDP ROS is only implemented in C++, and it has some quirks to it. So we might want to expand or actually simplify the protocol that is implemented, as well as investigate other transport mechanisms. One idea is to actually switch to something like 0MQ, which implements a number of them under the hood, like OpenPGM and UDP and TCP. Another idea is to totally get rid of masters altogether. They are a single point of failure, so no masters at all is also kind of like everyone's a master, depending on how you look at it. So much like peer-to-peer networks, if you have an address of a known peer, much like the master URI that exists now, you can propagate queries along the path of its neighbors that it knows about. This is something that came up in conversation with Dirk yesterday, actually. And one of the big open questions, at least for me, is whether or not transports should be built into ROS proper, or they should reside in sort of bridge or gateway nodes to reduce complexity of the ROS system itself, or should it actually belong inside ROS, and you get to choose the transport either at configuration or runtime of your node. And another big question that comes up a lot on the mailing list is whether or not we should share TF information between unreliably connected machines. Currently, what I do is I actually subscribe to, I have a TF listener that asks for TF messages and then puts it on a low bandwidth topic and then forwards it to the robots, which then insert it into their own transform tree. But maybe we want to think about an automated way of doing this. And I'd like to plug the multi-master SIG again. So if you have a particular use case in mind beyond multi-robot systems, if you have any ideas for multi-master beyond what I've mentioned today, you should join the SIG. We've moved from the mailman archives from the last SIG to a Google group, and this is the URL. So in summary, what we've covered what a master is, why you might want to have more than one. We've also covered an example foreign relay of a topic from one master to another. We've mentioned some future directions for multi-master and a plug for the SIG, of course. The multi-master Birds of a Feather talk will be happening right now after this talk during the lunch break. So anybody interested should come see me. Does anybody have any questions? Yep. So the question is, what has my experience been using these experimental tools on a regular basis? I found that they work great in a lab setting. I deal with my day job, I deal with a lot of fieldable robots, things like packbots and stuff like that, which we actually have ROS bindings for, by the way. And it doesn't work so well in the field. That needs to change if we're going to go beyond the lab. So especially robots that are literally deployed outside that don't have access to wireless routers and stuff like that. They have to deal with ad hoc networks with really low throughput. Those tools don't work very well right now. And some of the problems are with synchronization between masters. It just doesn't work that well. Right now, we're using XML-RPC, which is over HTTP requests, which is over TCP. It might not be the best choice. It works in a lot of cases. A lot of times you can just catch the exceptions when something goes wrong and keep trying over and over and over until you finally get your request through. But there's a lot of work to do. So the question was, would it be useful to have a machine in the middle trying to simulate bandwidth constraints between two machines? I think that's a great idea. I haven't tried that. I've been limited to just the hardware that I have at my lab. And to be honest, just changing routers makes a huge difference, and characteristics change all the time. So having something that could programmatically go through all those scenarios would be great. But, okay, so the question was whether or not you can basically cache the data that you want to send to a remote ROS system when the connection becomes available. I played around with toy implementations of this, but the main problem is when you depend on large pieces of existing ROS nodes that don't handle the exceptions for missing masters, a lot of bad things can happen. But that's probably just something that just needs to be fixed in those nodes that make assumptions about persistent masters. It's basically just the nodes get confused because they think that they're connected to a system and they're not, or vice versa. I could actually show you by, yeah, I can't show you by example, but the easiest way to think about it is if something went wrong on a ROS node that was registered to a master and it didn't unregister, and then another node tries to connect, it tries to open a connection to that old URI string that's in the master's dictionary, and nothing good's going to come out of that. So, does that help? Okay. Yeah. So in the foreign relay, what's that? Oh, so the scaling. The question is how to scale between one node and 3 nodes, and whether or not it's just the difference between writing more launch scripts. And it is, as long as you take into account bandwidth constraints. A lot of times you just have to relay to throttle topics and only forward those throttle topics just to make sure that you don't exceed your bandwidth and crash the network because everything's running over TCP. So the question was whether or not, I believe there's a heuristic for determining transport type without having to specify it manually. I think that could get complicated really quick. You might be able to do something simple with frequency and size of message, but that breaks down because you don't actually have any metadata about what type of use case that you're running in if you're just doing a heuristic approach. So say for teleoperation, you care about low latency, but not about reliability. You need to somehow specify that metadata in order for something like a heuristic approach to make a correct decision, if that makes sense. Any other questions?